Okay, so let's do some example problems here with the bearing capacity equation. So we are going to start with a footing, and the width of the footing is 2 meters. And we have a clay soil underneath, the water table's at the ground surface. Gamma saturated is 12 kilonewtons per cubic meter. It's a C prime of 10 kilopascals, a phi prime of 25 degrees, and we're going to say SU average equals 20 kilopascals. What do I mean by that? Well, we know that SU gets greater with depth. We spent, several weeks covering that topic. But for these problems, typically we use an average SU over the depth, 2 meters. In other words, B is 2 meters. We're expecting that it's this region of soil here, that is going to be sheared. So in other words, we can develop a shear plane that goes something like that, and that means the soil here is sheared, here, here, all these, across all these depths, we're going to be shearing the soil. And so we're going to take an average SU. You'll see this is typically the way these problems are set up, and it's a problem, but that's the way they're set up, and this is the way we do them, and we'll just recognize that there's an issue here. Now, we're going to say this is a strip footing, which means it perpendicular to the paper. It's infinite in theory, perpendicular to the paper, so this is not a column footing exactly. And we're going to analyze 1 meter of that. So it's infinite perpendicular to the paper, but we're going to analyze 1 meter perpendicular to the paper. So we call this a strip footing. This is our given table. I haven't shown the whole table yet. We'll get into that. But we have phi prime, NC, NQ, N gamma, and then I've put on some of the values for those right there. So this is given information. This is all given. That's given information. And so what we want, so this is the problem, is to find QU at t equals 0 plus. Okay, so this is a t equals 0 plus situation. And when we do that, we have to decide, are we EDS or are we tough? Well, are we effective drain slow or total undrained fast? Well, we are total undrained fast, right? Because it's at t equals 0 plus immediately after we loaded it. So we're assuming an instantaneous load, and we are taking the situation right after we applied the load. So if we are total undrained fast, and we have clay, then that means what? Then I'm concerned about this failure envelope. It's that failure envelope. So what does that tell me? That tells me that my intercept is SU, which means in my equation C prime is SU, and then that's flat, there's no angle, so I have a phi prime of 0. So, okay, so now this is the way I'm going to set this up for you to make it help you out a little bit, but basically, you need to know this equation. I don't really give that to you, but I set this up in this manner. I simply make a list of things, and your job is to come in and fill in the blanks. So, and then to multiply it out. So it's reasonably simple. So I say that I want you to memorize this expression, but I help you out a little bit by giving you the parameters here. So, okay. So let's fill them out one after another. C prime. Well, I look at my soil properties. No, this is where students have a problem here. If they don't think it through, they go, oh, here's C prime. It's 10. So they want to put 10 here, but it's not 10. Why? Because I look at my clay undrained failure envelope, and I have C prime is equal to SU. So SU is what? SU is 20. So I put 20 here, not 10. Okay, so be aware, you have to think through what is our failure envelope and put in the correct value for, because C prime in the equation really means intercept of the failure envelope. So, okay, so we got that. The other thing is, now we need to get NC. Well, how do I get NC? I get it from this, I get it from this table here. Well, the other thing I have to watch out for is I have to use the right value of phi prime. Well, if I look here, it says phi prime is 25 degrees. Well, if you don't think it through, you'd say, okay, I'm going to look for the values at 25 degrees and use these. But I don't do that because if I think about my failure envelope, I have, phi prime really means angle for the Moore envelope, and here the angle is 0. So I'm going to use these values of NC and Q and gamma. And so my NC, I go at 0, NC is 4, so I use NC as 4. And if I look at these other ones, N gamma is 0, N gamma is 0, NQ is 1, NQ is 1. So I can put those, once I make that decision of what my phi prime is, in a sense, then I can get my 3 bearing capacity factors and just write them in. Okay, so now notice if N gamma is 0, I'm looking at this term here. In other words, the way you need to look at this, there are 3 terms. 1 term, 2 terms, 3 terms, separated by plus signs. So I'm looking at my second term here. Well, if N gamma is 0, then I don't need anything here. That whole term is 0. So this whole thing is 0 if this is 0. So I'm going to write NA, not applicable, for B and gamma B. So we can skip those. So, in a sense, those sort of disappear. And I have the 1 here, so I need to come up with my Q. Well, what is my Q? Remember, the Q is the weight of the soil out here. So it is due to the weight of the soil out there. It's the stress due to the weight of the soil out there. Well, I didn't embed my footing, so there's nothing here. There's no soil there, so my Q is 0. So in other words, this term disappears, that term disappears, and my QU is simply 4 times 20 is 80 kilopascals. And that gives me the bearing capacity. In other words, I get my Q. And that means what? If I apply, if I end up with a stress, if I have a stress here of 80 kilopascals, I get failure. And I'll get this failure here, and this thing so I get failure. So now that's my bearing capacity. It's a stress, notice the units, it's kilopascals. So it's a stress. It's the stress that occurs that we need to have at the bottom of the footing to cause failure. So we like to have a big value here, okay? Because that means remember, it's bearing capacity. We like to have a large capacity. We like to have a large ability to resist our loads. So we like to have a big bearing capacity. We want that number to be big. That means that we have a strong soil, we can take big loads. So a high bearing capacity is good. Even though it looks like, don't get confused with this, because it sort of looks like a stress, right? It looks like a stress, and typically in engineering, we don't like big stresses. But just because it has units of stress doesn't mean that it is an applied stress or it's something like that. It's not. It's the capacity. We want to have a large bearing capacity. Okay, let's do this is the same problem, except that it's going to be at t equals infinity. So I should write this out. Same problem. but t equals infinity. So in other words, I want to know what is going to be the bearing capacity, 50 years from now or something like that. So that means what? That means I am now, when I do my EDS tough, where am I now? Well, I'm in EDS. I'm in EDS because it's effective drain slow. It's slow. It's a long time afterwards. So the excess pore pressures have dissipated. So now I'm going to do effective drain slow. So now I have to remember, what is my failure envelope look for effective drain slow? Well, this is my clay drain failure envelope. It looks like that. And that means that, well, C prime is C prime, phi prime is phi prime. So, in other words, my intercept is C prime, my angle is phi prime. So that's what that means. So then I can, there's fewer tricks involved. So same problem, but at t equals infinity. So again, if you want, you can fill in your NC, your N gamma, and your NQ, because I now know phi prime is phi prime. I've been given phi prime is 25 degrees, and there are my values there. So I just read them off. NC, NQ, and gamma, and I put them there. So very easy. So we can fill those in. Notice none of them are zero, so I don't eliminate any of my terms. So I now have my C prime. Well, now what? Oh, C prime is C prime, and it's 10. So now I can just use the 10. The B is 2 meters. Now I have to have a B. My gamma B, remember, is the buoyant unit weight. This is all saturated soil. There's my water table. So since it's saturated and everything, my gamma B, gamma buoyant, gamma prime is what? Is gamma saturated minus gamma water. That is the definition of gamma B, gamma buoyant. And we know that gamma B is also sometimes called gamma prime. So we have, as a result, this is gamma saturated is 12, gamma W is 9.8, we get 2.2 for my gamma B. And gamma we already got. Q is 0. Why is Q 0? Because again, it's on the ground surface. So I have no Q. I have no stress due to the weight of the soil out there because there is no soil. So my Q is 0, and we already did that, but that term drops out. So that term drops out because that's 0, and we get those two, we multiply those two, and we take 1/2, multiply those two out, and those three out, and plug everything in, and I get my value of bearing capacity of 230.87, 230 basically. So notice I can compare that numbers, 230.87, let's call it 230, and this one's 80. So what do we see? Well, the situation is much worse immediately after t equals 0 plus than at t equals infinity. So that's what if this is going to fail, it's going to fail immediately after we load it, more likely than it's going to fail, 50 years later. So, which is good, because we don't want things to be standing for 50 years and suddenly fail or something like that. Okay, so now we've got the same problem, but we're going to embed it 1 meter. So in other words, I've now put the same problem, same soils, everything, width of 2 meters, but we're going to embed it 1 meter. So now we've embedded our footings, which is what we're supposed to do. We really shouldn't be building things at the ground surface. So everything's the same. Now we're going to do this at t equals 0 plus. If I'm doing t equals 0 plus, then what do I use? T equals 0 plus condition, so t equals 0 plus condition. Well, I'm doing my I'm now TUF, and that gives me my failure envelope, looks like that. And so I have SU, and what does that mean? It's just goes back to the very first problem we did, which means that my angle is 0, so I'm going to use these values for my NC and Q and gamma. So again, N gamma is 0, so I don't need those two. NQ is 1, NC is 4. So I get all of those, and then all I have to do is, like we said before, the intercept is 20 kilopascals. I'm using the SU, 20 kilopascals right there. And then, but now, so all this is the same as what we had before, but now we have to look at the QNQ part of it. And so, remember, we are on TUF, total undrained fast. So this is total stress due to embedment. Well, I have 1 meter to the base of the foundation, and so my Q is going to simply be 1 meter times the unit weight, which is 12. So that's 12, so I go, so this is, 1 times 12. That's where it comes from. If we had embedded it 2 meters, it would be 2 times 12, but we only embedded it 1 meter, so it's 1 times 12. And, okay, so this is the total stress due to the embedment. There's different ways to look at it here. So in other words, I'm looking at this out here, and if that's confusing to you, so I look at what's happening here. I don't look what's happening here, okay? If that's confusing to you, another way to look at this is it's the total stress at the footing depth at t equals 0 minus, which is t equals 0 minus is what? Before anything is built. So you can look at it this way is another way to look at this Q. So now what do? I simply add this last term, which is 12 times 1. And I get the 4 times 20 plus 1 times 12 is 92 kilopascals. Okay, I will describe that later. For the time being, I'm going to let it go. So notice 92 kilopascals, because we embedded it, it was 80. 4 times 20, it used to be 80. So by embedding our footing, we have increased the bearing capacity. Then that's a good thing. That's one of the reasons we would embed our footing. Okay, so now we're going to do the same problem at the t equals infinity condition. So again, we're going to embed it 1 meter. So we have our 1 meter embedded, but now we're going to do t equals infinity, which means what? Now we are effective drained slow. Okay, so if we are effective drained slow, then that goes back to what we had before, which is our failure envelope looks like that, and so what do we have? C prime equals C prime, and phi, the angle is phi prime. So we now have that failure envelope, and again we can get our values, which we put in there. And so this stuff is the same. The C prime is going to be, C prime is 10, and the B is 2, and then its gamma B is 9.8, again because it's effective drained slow. So we're effective, that we're going to get the effective unit weight. We're going to use the gamma prime there. So, but now what do we do with the Q? Well, again, we are what? Effective drained slow. So that effective means we get effective stress at the footing depth, not total stress. So we put in effective stress. So it's what? 1 times 12 minus 1 times 9.8 is 2.2. So that is our Q. And that is, the NQ is given as 10.7. It's over here. So what do? Now I just simply plug into my expression, and then you can look at this, and it's just a matter of plugging it in, and now I get 254 kilopascals. And what did we get, before we, so 254 if we embed it, and what did we have previously? We had 230 when it was not embedded, when the Q was 0. So again, we increased our bearing capacity, which is a good thing. That's what we want. Again, I will describe that later. Okay, I'm going to stop then.